The Signal Acquisition, Modeling, Processing, and Learning SamplLab introduces joint radar communication systems. Imagine a future where cars can not only drive themselves but also communicate with each other seamlessly. This is where joint radar and communication technology, also known as dual-function radar and communications, comes in. Dual-function radar and communications, or DFRC, combines radar and communication functionalities into a single system over the same bandwidth and time. In autonomous vehicles, DFRC can detect objects like other vehicles, pedestrians, and obstacles using radar. At the same time, it can communicate with other vehicles or infrastructure using the same hardware and bandwidth. This technology allows vehicles to share information in real time, such as road conditions, traffic updates, and upcoming hazards. By sharing this information, autonomous vehicles can make better decisions using less resources, improving safety and efficiency on the roads. At the SamplLab, we developed 5 different strategies for DFRC. The first strategy is called Multi-Carrier Agile Joint Radar Communication, or Majorc. Majorc is a strategy that enables both detection and communication using the same waveforms transmitted from a linear antenna array. This array consists of 16 elements, with 8 for transmitting and 8 for receiving signals. Digital information is embedded through a method called Joint Spatial Frequency Index Modulation by the selection of transmitting antenna subset and carriers. Majorc seamlessly integrates with traditional pulse radar systems without reducing radar performance. We demonstrate the prototype using commercial FPGA boards and radio frequency modules. The Majorc can achieve a communication rate of 125 kilobits per second and demonstrate comparable performance to dedicated communication antennas, all while maintaining radar functionality. The second strategy is called FMCW-based Joint Radar Communications System, or Frack. The Frack system, derived from Majorc, achieves lower cost and complexity by using fewer radio frequency modules and narrowband frequency modulated continuous wave FMCW signal. It activates only a portion of the antenna elements during each pulse. By combining FMCW signaling with phase modulation, digital messages can be transmitted. We show the Frack system using an inexpensive commercial millimeter wave radar development board, which doesn't require hardware modifications and implements our algorithm reliably. Our system is controlled via a user-friendly GUI for easy configuration of radar and communication subsystems. The communication side is handled by a separate PC server, detecting and processing received messages, while the radar receiver processes radar echoes to reconstruct target scenarios. The waveform generator ensures synchronization between the transmitter and receiver for seamless operation. The Frack prototype achieves a communication rate of 34 kilobits per second. The third strategy is called Full Duplex DFRC system. To realize simultaneous bidirectional information transmission and target detection between 2 moving vehicles, we further propose this full duplex DFRC system. It utilizes uniform transceiver arrays to transmit an identical waveform for both detection and communication. Full duplex functionality is attained through frequency modulation during transmission and demodulation during receiving. A user-friendly GUI allows for system configuration and result analysis in both simulation and real-time modes. In simulation mode, users can adjust communication bitrate and SNR and simulate DFRC system and target positions. In real-time mode, 2 DFRC prototypes exchange messages and detect targets concurrently. DFRC achieves high-speed full duplex data transmission at a rate of 8.5 kilobits per second. The fourth strategy is called Spatial Modulation-Based Communication Radar, or Spacore. The Spacore system is different from previous approaches by employing distinct waveforms for communication and detection through different elements within the same antenna array. This strategy enhances communication rates by incorporating additional data bits in antenna selection. Communication and sensing operate concurrently, with antenna allocation patterns dynamically adjusted through spatial index modulation over time slots. Information is encoded into active antenna element selection and modulated through symbol constellations. The system can be deployed using conventional communication system architecture. A multi-antenna prototype has been showcased using commercial FPGA boards and radio frequency modules, achieving a communication rate of up to 4 megabits per second. The fifth strategy is the Single Antenna Joint Radar and Communication, or SAJRC. While previous methods focus on joint strategies at the transmitting end, SAJRC aims to mitigate interference between radar and communication signals at receivers. SAJRC simultaneously estimates target parameters and decodes communication signals by leveraging the sparsity of radar echoes and prior knowledge of communication constellations in the time domain. The hardware prototype comprises a PC server, which hosts a GUI for setting signal parameters, generating combined waveforms, and processing received signals, a hack RF1 for transmitting combined signals, and an oscilloscope serving as the receiver. Compared to conventional spatial domain-based methods, SAJRC demonstrates superior performance when radar targets and communication users are at similar angles to the base station. It achieves a communication rate of 500 kilobits per second. At the SamplLab, we are continually working to refine DFRC technology to make autonomous driving safer and more reliable. In the future, this technology can also be used to enhance location information in 6G wireless networks. To learn more about our technologies, please visit SamplLab website.